This unit is a rehearsal of basic set theory. It is needed to fully understand the lecture on input-output automata, which describes model of distributed system. It is only needed if you are not familiar with set theory, or you just learned that in school but you forgot. So we are going to talk about sets, relations, and transition systems. So sets contain elements, which themselves can be sets. So here is an example of a set A containing 3 elements: the element A, the singleton set D, and the singleton set A. Sometimes we do not want to list all the elements of a set. Then we can write the set by a property that describes the elements of the set. So here is the case. So this description says it is a set of x's such that each x has some property. For example, the set of x's such as x is an even number. So this is a set of all even numbers. Now observe that order is not important in a set. And also the number of occurrences of the same element is not important. So the set AB is the same as a set A, B, and also the same as a set BA. Whereas, which is important, that the set of A and the singleton set that contains A is not equal to the set A. Sometimes we do not talk about sets, but we talk about multi-sets. And what are multi-sets? It's a construction, a collection where the number of occurrences are important. So if we are talking about multi-sets, the multi-set A and B is not equal to the multi-set A, and B. In fact, multi-sets are functions or mappings that in fact describe the following mapping: that A maps to two elements of A, and B maps to 1. So that's what we are saying here. Formally, a multiset is a function that maps elements of its domain to a range of positive integers. That's what we said. So the multiset A, and B is that set that we just mentioned. If an element X belongs to a set S, we use this notation to say that X is an element of the set S. And we use this notation for the empty set. And what this means, the empty set says that for all x's, the following is true: that this empty set does not contain any x. We use the following notation for Cartesian product. And what is a Cartesian product? Of two sets, we have the set x and the set y, and this is notation for a Cartesian product of two sets. And it is the set of the pair AB, the set of pair AB, such that A is element of x and B is element of y. Sometimes we write it also like this, like A, B to denote the pair, and then we said, okay, A is element of x and B is element of y. So here is an example. If x is a set ABC and y is a set CDE, then the Cartesian product is the combinations of all elements from x with all elements of y. So, for example, we take A and combine it with all elements of y. We get this element, and this element. We take B and combine it with all elements of y. We get this element, and this element. And we take C and we combine it with all elements of y. We get these elements. And each one of these is a pair. And in pairs, order is important. So, for example, in this pair, A is the first element of the pair, and C is the second element of the pair. If we have n sets, for example, x1 to xn, so we can use this notation p xi to denote the Cartesian product of all these sets. Now, let us look to union. What does it mean for a union on operation on two sets? It is saying that it is the set of x's such that x's is either element of the set x or x is element of the set y. So, for example, if x is a set of AB and y is a set of A, D, and E, then the set, which is a union of x and y, will include A coming from capital X, large X set, and B. A here is repeated, so it will also include then D and E. Now let us look to operations on set, and especially ordering operations. So sets could be ordered by a subset relation. So a relation, it is a relation between two sets. So the subset relation between two sets x and y, which says x is a subset of y, means that if A is an element of x, then A is also an element of y. We are really defining the subset relation, and that holds for all elements A of x. So you can see here the set AB is a subset of ABC because each element in the first set is also included in the second set. And the subset relation, as we defined, also includes equality. So if two sets are equal, also one set will be a subset of the other and vice versa. So ABC is a subset of ABC. And here is an example which it is not the case. So AD is not a subset of ABC because D is not a subset of ABC. Sometimes we also talk about proper subsets. And proper subsets means that we can define it like this. X is a proper subset of Y if and only if, that is the definition. X is a subset of Y and X is not equal to Y. So a proper subset excludes equality. So let us look to binary relations on a single set. So a relation X in general is always a subset of the Cartesian product of the set with itself. So which would mean a relation X itself is a subset of S times S, and this actually can also be written S squared sometimes. So here's an example of a binary relation. S is a set A, B, D, E, and this is a binary relation. It is the set of pairs AA, BE, and EE, and that is a subset of the Cartesian product of the set with itself, or the set square. And as we said, we can write pairs this way too. Now there is a number of important binary relations on set. The first one is the partial order, or poset, sometimes it's called. So a partial order is actually a pair, a set, and a binary relation, and sometimes we write it this way, which for each x and y in the set X, we have the following properties. And these are properties describing the partial order. First, it says that partial order is reflexive, which means for any element x in S, x is less or equal x. That is reflexivity. Then we have the second property, which is anti-symmetry for any elements x and y in S. If x is less than y and y is before x also here, then it means that we are talking about the same element. That is anti-symmetry. And then we have transitivity, which says if x is less than y and y is less than z, then x is less than z in the partial order. So the pair x, z is also in the partial order. So it's element of the partial order. It's element of that relation. So here's an example of partial order. We have this set which contains A, D, F, and G. And we have the following partial order relation. First of all, we have to satisfy reflexivity. So AA is in the set, DD is in the set, FF in the set, and GG in the set. And then we have A is before F, it's this arrow. F is before G, it is this arrow. A is before G, this is a transitivity relation. And D is before G, this is this arrow. Observe in partial order some elements are not related. For example, this element and this element cannot be compared. There is no order between these elements. That's why it is called partial order. When arbitrary couples of elements can be compared, then we are talking about total order. And that's what we can see here. So what is a total order? It is again this pair S and a relation, we call it here also less than, which satisfy all the properties of partial order: reflexivity, anti-symmetry, transitivity, and one more property which called dichotomy or totality, which says for each element x and y, either x is before y or y is before x. An example of a total order is here. This is our set. And basically this element has to be put in a straight line. So here is the relation, the total order relation. We first satisfy the reflexivity. And then we are saying that A is before F, F is before G, A is before G because of the transitivity, D is before G, again, because of the transitivity. This is already repeated, we don't need it. And then we have also D before F, because of transitivity. And then we have D before A. We covered the relation between all the elements in the set S.